Okay, so today is our final exam review. This is technically the last lecture. Last time you'll really see me live unless you come to office hours on Thursday or we set up an appointment or you send me something on Slack or something like that. But this is our last sort of formal lecture because if we look at the schedule moving forward, then we see that, you know, what remains here is that the only other assignments that you have to worry about are on, there's a muddiest point, your final muddiest point that's coming up here on this upcoming Sunday. And we're not going to go over anything new this week. And so you can focus that muddiest point either on the final exam or on your preparation for the final exam or on the semester as a whole. And the prompts for the muddiest point have been adjusted to remind you of that. Your final project is due tomorrow at 11:59 p.m. And so those, that's both your video presentations as well as your reports. And then at 11:59 p.m., then the Canvas will automatically randomly assign all of the submitted presentations and all of the submitted reports to anonymous peer reviewers, so that so that's why everyone needs to have them in by 11:59 for that random assignment to be made and make it all balanced across everyone. And then every one of you will be assigned one report and one presentation, not from your group. And those peer reviews will be due Saturday night. And just as a reminder, because I got a couple of questions about this, I posted an announcement, which I've shown up here, that reminded you that in the final project report assignment, where you go to actually submit your final project report, then it actually details, and this is also detailed in the final project document, which goes over kind of the whole process, that we're expecting a very specific format for your final project report. So not only is it no more than 4 pages, excluding title, page references, and appendix, but we're expecting that there's going to be a number of labeled sections, and the rubric for the final report is going to expect those. And so if I scroll down to the end of this page, there's a rubric down here, and we can see that the rubric actually looks for those specific sections. So that's a rubric that each one of you will look at when you do your peer reviews. If I were to recommend how to write this report, eventually, once you get accustomed to writing these things over and over again, then you write the executive summary first, and that sort of gives you an outline of the rest of the report, because this executive summary sort of stands alone. It's like an abstract. But when you're just starting with these things, a common bit of advice is to actually write the results section first, because that's where you put all of your figures that you want to use to make your argument. So you put your figures in there and you explain the figures, and then you actually, there's a kind of a toss-up whether you write that section first or the conclusions first, but you can kind of write those hand in hand together, because that helps you sort of say what you were trying to say. And so you can sort of, in your conclusions, that's kind of where you're going to discuss how your results relate to the kind of final conclusions that you're making. And those results and those figures land in the summary results section. And then once you have those things up together, it'll kind of be really in your head, like all the motivation and all that sort of stuff. And so you can then go back and start writing these other sections. And so this model and simulation methodology section, this is where you actually put your simulation model in, and you can explain effectively this section is, based on the figures that you needed to generate here, that's where you kind of have to sort of say, well, where the heck did you get those figures? Well, that's kind of what you talk about in your model and simulation methodology is this simulation model that will be used to generate these figures that you use. And then from there, you can go back and say, all right, well, then why did we even build that simulation model, where there's your problem description. And then all of those 4 sections together, problem description, model and simulation methods, results, and conclusion, those are sort of summarized in one paragraph in your executive summary, which should otherwise stand alone. So that's one way you can think about writing these things. They will be written, they'll be positioned in this order, but you don't necessarily have to write them in this order if you're having trouble getting started with this. But we're only looking for 4 pages. It can be double spaced if you're more comfortable with that, but it's perfectly fine for it to be single spaced. The main figures that you're using, which are, you might have a figure of your simulation model, or maybe a couple figures will be in this model and simulation methods section. The actual figures of your results that you generate with your sim will be in this simulation results section. And if you're having trouble with space, then you can do things like you can go into Word and you can have it wrap text around those figures. Each figure should have a label and a caption. So you can say figure 1, model of, Phoenix water system or something like that. And then in your actual text, you can then say, figure 1 shows our, the model that we used to, et cetera, et cetera, et cetera. So that's, make sure you've got labels on figures and labels on tables, and then refer to those labels. Don't say like, as shown below, and then just have a figure down there. So that's, I just wanted to highlight that because I wasn't sure if it was totally clear that this 4-pager really has these specific labeled sections that we're looking at that's supposed to actually make it easier to grade as well as easier to write. Okay, so that's the final project stuff that's coming up. And then the last kind of, and I see the question in the chat, and then the last sort of assignment is that there are these student evaluations, both of the course, which were sent out to you from the university level, as well as these TA evaluations that they implemented at the sustainability level. And both of those links are in the top left corner of Canvas. And so if I would bring back Canvas here and you scroll to the nav bar here, then there's a course evaluations and a TA evaluation form, which you can fill out up here. I think these course evaluations go away in like 2 days. So if you're interested in filling those out and giving feedback, then please do soon. Otherwise, the only feedback I'll get is from places like Rate My Professor, which tells me, which always makes me very sad as I learn about my gigantic ego and how I'm an ivory tower academic who has no business being in a classroom, if I remember the common things that are said about me there. So it's nice to get a little more constructive feedback, and then usually that constructive feedback does end up coming through these student evaluations here. So appreciate those. There are questions here. Do all team members have to submit the report and the video presentation? Both of those are group assignments in Canvas. And so you should be able, if one team member uploads them, it will automatically populate it in all of them. And so when they end up getting graded, one grade will go to everybody. So you just, you don't all have to upload it. You can just upload the one report and the one presentation. And when I say the one report, I'm also expecting with your report you to upload your model file. So you should upload to the final project report here. You should upload that. We're looking for at least 2 files, a doc or PDF file, and your model file or Insight Maker file. And so both of those, one person in the group can upload. And as you can see, one group has already submitted their report, and it tells me that 4 submissions are there, and that's because it's a group of 4. So one uploaded and it populated on all 4 automatically. Same thing with the presentation. So that's kind of the schedule of assignments moving forward. And we'll talk about the final exam here today. I'll stop for questions here in a second, but I just wanted to get through that slide just to make sure we're all know what the schedule is here. So that on Thursday, in 2 days, we will not have a class. We will not be meeting. You don't have to see me anymore for the rest of the semester. And instead, it'll be just like stage 1 of the midterm. The final exam is out there. It will be released at midnight Thursday, early Thursday morning. So you have all of the 24 hours to individually start that exam. And whenever you start it, the clock will start ticking and you'll have 90 minutes in order to complete that exam. And then after that 90 minutes, then it'll disappear from you. You won't see your score. You won't see a solution set. But Tuesday of finals week, the collaborative stage 2 will be released, and that collaborative stage 2 has exactly the same questions, and but that one is the one that you can work on with your classmates, and you can use your own notes. You can use materials that I've provided on Canvas. You can use your textbook, and so it's exactly the same as the midterm. And that one is not timed, just like the midterm, but you have that full 24-hour period to complete it. So Tuesday night at whatever 11:59 p.m. it disappears, and you won't be able to submit it anymore. But you'll be able to work on it all of Tuesday. All right. So before we talk specifically about the final, are there any other questions that I can help you with about the final report, the presentation, the schedule moving forward, any administration stuff? All the requirements clear? Okay, great. Just wanted to provide a little bit of pause there. All right, so basically I'm just going to go over basic formatting stuff, and then I'm going to open it up for questions. If you have no questions, I can start through some slides I prepared just to remind you of some of the content we've gone over. But then you can stop me at any time to ask me those questions or get clarifications. So again, this final exam, it runs very similar to the midterm, except it's comprehensive. It goes over the whole semester material. So this is a two-stage exam. I'm allowing you one two-sided handwritten formula sheet. And I believe in the actual instructions, I actually allow you like two blank pieces of scratch paper as well. And so in the respondus portion of it, you'll have to show both sides of all of your sheets of paper to the camera. It's comprehensive, so it goes through all of our units, A through G, but it is the same length as the midterm. And so it is designed for you to be able to finish in a class period. So that's why I've got it set at 90 minutes. The 90 minutes is really supposed to be like 75 minutes plus 15 minutes for technical issues. And so, so that's what we're kind of going on there. And so so it's also going to be the same length. So it's, I think if I remember correctly, on Canvas, it's 25 questions and 35 points. And so some of those questions are going to be matching questions and things like that. So it's going to be very similar to the midterm format. If you've taken the sample final, it will be very similar to that final. I think the sample final might actually also be 25 questions and 35 points, are really similar to that. So the sample final is real similar to the final that you'll end up seeing in format and in structure. So that's basically it. The only thing I will remind you of is there's still a handful of people who haven't taken the final exam lockdown browser compliance test. And that's an important thing to take because you won't be able to get access to the final exams until you take it. And you may not have noticed it, but you actually get a tiny little bit of credit for getting that. And so once you take that, then you immediately sort of get, you know, for free some final exam credit just for getting for finishing that compliance test. And then once you take that compliance test and show that you're ready for the lockdown browser with the monitor, then it'll open up that final exam module, which has you know, a practice exam that you can take on Canvas, a sample version of it in PDF form with a solution set, and then a whole nother sample final exam blank as well as its solution set. And it has all the notes or all the slides for this lecture here. So make sure you take that. It'll unlock a lot of study materials. So from this point on, the organization of this review is, if we want to go forward with these review slides, all I've basically done is gone through all of the lectures throughout the entire semester and grabbed the kind of greatest hit slides. And I've organized them with kind of the newest stuff first, or kind of the oldest, newest stuff first. And so the post-midterm units, unit E, F, and G come first, and then I jump to the pre-midterm units A, B, C, and D. The only slides that I've added are at the beginning of every unit. I've added some learning outcomes, which are basically a study guide for each of those units. These are also echoed at the top of each one of the unit modules on Canvas, and then the whole collection of them echoed at the top of the final exam unit module on Canvas. So I can continue on with this and try to hit some of these. And the reason this is bolded, by the way, this Introduction to Numerical Simulation Dynamical Systems, I would say that of the pre-midterm content, I mean, you're gonna see questions about what is a model sort of stuff and some like causal loop diagram fundamentals. But I'd say that this numerical simulation of dynamical systems, that's sort of the most important pre-midterm material. It's kind of has the most depth in it. All right, so at this point, I'm happy to move forward with that, or I can stop here. And if you have accumulated some questions, we can field them now. If there's some sort of exercises we can work, we can do that. Or if you don't have anything now, I can march forward, but then you really should just feel free to interrupt me, put things in the chat, unmute your mic, and so on. So I see a question in the chat. Will there be more post-midterm material than pre-midterm material on the exam. It's hard for me to say that because the post-midterm material builds on so much of the pre-midterm material that it's hard for me to disconnect them. It's not like a history class where we're like pre-midterm, it was from this year to this year, and post-midterm, it was from this year to this year, and the final exam is going to have a certain blend of these years, a certain blend of these. So like, you know, you're going to see like, you know, stock and flow diagrams that will be more complex, which look like post-midterm stuff. But I mean, we learned about the stock and flow diagrams pre-midterm. So I don't mean for it to sound like a cop-out, but it's really hard for me to weigh those two things together. Because to me, really the post-midterm stuff is just building on the fundamentals we got pre-midterm. I won't ask you, I will tell you this, that I won't ask you specific, like this isn't an epidemiology class. This isn't a class on the world politics of oil. So I'm not going to ask you a question like, who is the swing producer in OPEC? Because that doesn't really relate to system dynamics modeling. I could ask you things like, in the SIR model, if you focused on the transition from susceptibles to infectious, there was a flow that that depended upon the number of infectious and the number of susceptibles. Like I could ask something like that, but I would sort of line it up and then ask you a question about the dynamics of those interactions, not specifically about the interactions. So I wouldn't ask you what the basic reproduction number is, like the R naught number. I wouldn't ask you to define that because again, it's not an epidemiology class, but I might use the SIR model as as something that helps us set up a question to ask about the dynamics of the SIR model. So any other questions or concerns? I'll just pause here and then I'll start rolling forward through these slides. But again, with you encouraging you to unmute or chat or post things to the bit.ly questions page here, which I will double check that nobody has put down any questions on right now. Okay, it's blank right now. And there's a question in the chat. Yeah, and so Eric responded. So Eric is going to hold a Zoom call during the normal, I think, class time. And so I think like the midterm, maybe Eric, if he can post some information about that. Yes, thank you, that'd be great. Yeah, so Eric will send out details over the weekend. So basically for those that weren't aware, during the midterm, Eric will sort of set up a virtual meeting space so that everyone knows that it's there, so that you can kind of come together if you want to work on the exam at a particular time. You are also perfectly welcome to do that. You don't have to use any of the platforms that I provided, but you can also, if you like, similar to the midterm. I think in the midterm, someone posted on Slack that they had set up a room elsewhere. And I promise you that I will not go and spy on you in those other rooms. So if you would like sort of a private space away from me to work with your classmates, then that's fine with me. I trust you. You guys know the rules of the exam and everything like that. If it makes you more comfortable and less anxious, then more power to you. All right, so any other questions, or should I just roll forward here? All right, so again, I'm just gonna march on forward here. I'm just trying to kind of exercise demons. If anything you see on the screen raises a question, even if it doesn't have to do with what's on the screen, just let me know and we can work through it. So at the beginning of each one of these slides, I've got the learning outcomes that I've also listed on Canvas. And so if you go to Canvas into Unity, on the Unity module at the very top of Unity, there's like a Unity study guide, and it lists, the study guide is basically the learning outcomes. And so so that's what I've kind of prefixed each one of these review slides here. So if we go down through Unit E, these are the things that I really want to make sure that you know coming out of Unit E. We talked about probably a lot of other things in Unit E, but these are the key things. So are you comfortable with fixed delays and smoothing delays? You know, those are things that, you know, probably you should make sure you're comfortable with. How do you feel about graphical lookup tables? Like those are other things I think you should be, you know, important, you know, that are important, and so on and so forth. And so Of course, some of these learning outcomes are going to be practical. So the ones that say, that refer to using VinSim, like, ability to, I don't know, I can't think of a learning outcome right now off the top of my head that might use VinSim or Insight Maker, but the ones that you could only demonstrate by actually building a model and running it for me, then those are going to effectively be assessed when you do your final project and final presentation. I'm not going to have you like build a virtual model in the final exam. I might show you a VinSim diagram or an Insight Maker diagram and ask you about elements of it. So you should be able to read those diagrams, but like, I'm not going to say like, which menu in VinSim do you find the time step setting? That's something that I won't ask you on the exam. So like those like operational details of how to get VinSim running are not the things that I'm going to assess you about on the exam. Okay. I do say, basic familiarity with the SIR model and the BAS model, because I could ask you questions using the SIR model and the BAS model to help us talk about dynamical systems. All right, so these slides, you've seen all these slides before. So this is just a reminder about lookup tables. So I'm not going to go through each one of these as slowly as I did the first time. I'm just flashing them up there to remind you what a lookup table is. And if you have questions about, I never quite understood, how to make these lookup tables work, this would be a great time to bring those up. So, our first lookup table that we saw came out of this fishery model, this net regeneration, and the lookup table was really just meant to be a graphical representation of the relationship between fish density and net regeneration. You could come up with a formula, that would be like density times 1 minus density times some constant. And that would give you a relationship that if you graphed it would look similar to this relationship here. But instead of coming up with that formula, you can just draw the relationship, and that relationship allows you to specify how VinSim or Insight Maker should generate this relationship for you, so that if a density like this intermediate density pops up in your simulation, it will make sure that it corresponds to this intermediate regeneration rate over here. So you only have to specify the points at the dots, and it fills in all the rest. It's kind of what we got here. And that's the basics of lookup tables. The other big thing about lookup tables is we talked about lookup tables are often used to use with a time shadow variable or an Insight Maker. You can just choose it as the input of the lookup table. And that allows you to, to generate these seasonal patterns, so that if you have time going into the lookup table, you can say as time is marching on in a linear fashion, then some seasonal pattern might oscillate. So temperatures get hot in the summer, they get cooler in the winter, hot in the summer, and so on and so forth. And so that is a pattern that is tied to time that you can then use a lookup table to draw that pattern in. So that's another way that we commonly use these lookup tables. And like I said, it's either a shadow variable in VinSim, or it's just hard-coded as the time in Insight Maker. And that's all. I'm just kind of, again, borrowing from those samples or those slides there. And then that allows us to do things like this. And so this is an example of using a lookup table with a variable interest rate that varies over time, so that we can see that the savings account balance here is always growing, but it grows at different rates. And those rates change over time. And that's because inside this, there's a lookup table, which is saying for this time, use this interest rate. For this time, use this interest rate, and so on and so forth. So that's like my brief refresher on lookup tables. Does anyone still have questions on lookup tables? I know a couple of people in the Muddiest Points mentioned that now that they've been using lookup tables in their models, that things that were clearer before seem a little murkier. They have a hard time figuring out how to make use of lookup tables. Where I know other people have said that since using them, they're now clearer. And so I think things have shifted in both directions. So is there anything I can help you with regard to lookup tables right now? All right, well, if anything comes up, again, please stop me as we move on. The other thing that we talked about in Unity were delays, and we talked about fixed delays and smoothing delays. So it's important to know the difference between those two types of delays and try to think of examples of those. And so we had this kind of in our traffic example here. Then if we kind of view these three regions, the A intersection, the B intersection, and the length of street going from A to B, then we can think about there's a process where when you go from intersection into the street, it's kind of a stretching out process where the order of the cars might kind of change. Certainly the spacing of the cars will change. And so if we are modeling the cars that are entering the intersection, we would view it as a smooth version of the cars that are waiting to be released from the intersection. So we've got the cars waiting at the intersection and the cars entering that street block, and we view that as a smoothing delay. So if you know the cars waiting at the intersection, then you can run that. So basically the light turns green and you kind of know that in theory, all the cars that were waiting at the light should be able to enter this street block immediately. But in reality, they don't enter it immediately. The cars in the front immediately enter it. The cars in the back kind of wait, so that over time, instead of getting this bolus, this large group of cars that immediately move into the block in between the intersection, you instead get a small group of cars that move in, and then gradually over time, all those cars eventually move in, but it's spread out. And so that is an example of a smoothing delay. It spreads traffic out and possibly even changes the order of things a little bit. But then if we view the cars moving across this block, once they kind of come to a steady state distance between them, they stay roughly in the same pattern. And so if you know how many cars are entering the block, then you know how many cars are going to be at the block roughly a certain time later. And so if you know the speed limit is 25 miles per hour, then you can figure out that, well, a minute later, you know exactly what cars are going to be here, because they're the exact same cars that were far enough, that were back, if you were to kind of do the calculations to figure out how far cars can travel at 25 miles per hour. So that's the idea, is if you've got this bolus that's just moving through and not really changing much, that is represented as a fixed delay. So, so that's the two types of delays you want to model here in VinSim. So the smooth response greatly changes the way things look. The fixed response just shifts them later. Those are our two types of delays. There are other types of delays. So fixed delays, there are things like schooling behavior, a type cluster of animals like a school of fish, age structure and populations. And so those in first grade, if there could be 100 students in first grade and 75 students in second grade. And the year after that, there'll be 100 students in second grade and 75 students in third grade. A year after that, there'll be 100 students in third grade and 75 students in fourth grade, and so on and so forth. So in that case, the number of students in each grade is not sort of changing its shape, but it's just moving year after year. And that's the example of a fixed delay that you would model in your models. All right, so there are questions about the fixed delays. And we can contrast them, of course, with smoothing delays. And so maybe I should ask for questions after the smoothing delays. My example of smoothing delays that was not car related was like food entering the bloodstream, or nutrients entering the bloodstream. Food hits your stomach all at once, but nutrients will diffuse into your bloodstream after a certain amount of time, that some nutrients will enter sooner than others. And so even though food hits your stomach immediately, the nutrients take a while to actually diffuse into your bloodstream. So it smooths out that edge that plop of food in your stomach creates. And so that's a smooth output there. So that's what we say, the input changes instantaneously, but the output is much more sluggish. It's not unlike a toilet flushing, where right after a flush, you desire the water level to be at the top of the toilet, but it can't, And so the valve causes some water to come in immediately, but the rest of the water has to wait a certain amount of time. And so even though the desired water level jumps up immediately, the actual water level takes a while to rise. So that's another example of a smoothing delay. And in, in all of these systems, the delay is effectively a characterization of the sluggishness of a system. And we generically test these systems for their sluggishness using something called a step response, where we put in a step, which is like this desired change. I suddenly desire the water to go from 0 to 100% in the toilet. And if we measure how long it takes for that water to rise or those nutrients to enter the bloodstream, then it turns out there's this magic number here where the time it takes for the actual output to rise to 63.2% of its final value is this so-called time constant. And that's the thing we use as the characterization of the delay. So when you say, what is it? A fixed delay, it's obvious what the delay means. It's just take exactly the pattern here and shift it exactly that amount to the fixed delay, but exactly that amount over. And you say, well, what does it mean when the input and output don't look the same? Well, when the output rises to 25% of the, or to 63.2% of the input, then the time it takes to do that is the so-called time constant. And then that is, and that's what we use to characterize the delay of these systems. Okay. And I think I've got a couple more slides that just kind of elaborate on this, this whole thing here. I don't want to go belabor this stuff too much. I guess maybe I will bring up the examples here of systems where we'd expect to find smoothing delays. And so these are systems with inertia. So you know that if you put a force on a system, so like if you start accelerating in your car, the velocity doesn't change immediately. You have to wait for the velocity to rise up. And as similarly as your velocity goes up, your position doesn't change immediately. You have to wait for the position to change. So the relationship between force and the change in velocity there is this mass. So mass is sort of represents the sluggishness here. Heat capacity. So Eric talked about heat capacity in terms of water. And so we know that if you've got a mass of air in front of you, then it takes a little bit of heat to increase that temperature of the air. And then likewise, when the temperature of that air around it goes down, it quickly dumps all that heat and it cools down to the around it. With water, you can dump a lot more heat into it before it changes its temperature. And then if you make the temperature less around that hot, thing of water, then it's going to dump a lot more heat to the outside environment as it gradually cools down. And so it stores heat, and the ability for it to store heat means that there is a sluggish relationship between heat being transferred to the water and temperature of the water. And we can model that using a smoothing delay, this sluggishness. Bucket diameter. So similar thing, if I'm dumping water into a bucket, the bigger the diameter, the more sluggish the height changes. And then in a social setting, stubbornness. The more stubborn a person is, the more I try to get them to change their opinion, the longer it will take for them to change their opinion, and so on. So those are all things that we might model with smoothing delays. So are there questions about fixed and smoothing delays? Even the process of asking questions, if it was the case that all of you came up with a question after 5 seconds of thinking, then I would say, are there questions? And then I wait exactly 5 seconds, and then I would get 30 questions or 23 questions. But, and that would be a fixed delay. If I were to model the dynamics of the classroom, then that's the way I would model that. Instructor asks a question, fixed delay, 5 seconds, answers generated. So whenever the instructor says questions, then I would expect answers to come 5 seconds after that. But in reality, questions are generated according to a smoothing delay. Some of you will immediately have questions. The rest of you will have to think about it for a long amount of time. Some of you effectively won't have a question. It's like having to wait an infinite amount of time. So when I ask for a question, I might get one question immediately, 2 questions a little bit after that, 3 questions a little bit after that, and then things kind of fall off. And those things end up having sort of a sequence and they kind of spread out. And so that if I went to model the dynamics of a classroom, it would probably be wrong for me to use a fixed delay in Vensim or InsightMaker, but I could use the smoothing delay, and that would show how quickly questions are generated in the classroom. And then I could model how long it takes to service all those questions, and it would really be important for me to get that fixed versus smoothing right to get that model right. So with that in mind, now that I've given everyone enough time for their smoothing delays to come up, are there any questions before I move on to SIR models? Okay. And glad to hear that example was helpful. Another example I can give you is in the SIR model, whenever someone is infected with a disease, yeah, now I'll get to that question in just a second. That's a great question. If whenever someone is infected with a disease, it takes, some people get well soon and some people take a long time to get well. And doctors give us an average amount of time for someone to get well. On average, it takes people 7 days to clear the flu. Some people are going to take 8 or 9 days. Some people are going to take 4 days, but on average, those individuals take 7 days to clear the flu. In reality, doctors probably give us a conservative estimate, but modelers need the average value. So on average, how long does it take someone to clear the flu? Some earlier, some later. And so this process of going from infectious to recovered, although we explicitly modeled this process using our own stocks and flows and so on, we could have modeled recovered as just a smooth version, a smoothing delay version of infectious, because that's really all recovered is that whoever is infected will, after a smoothing delay, become recovered. That means some of them will become recovered quickly, some will become recovered slowly, but to model the average behavior, we can capture that with a smoothing delay. There was an excellent question in the chat. Can you explain the graph quickly with the 63.2% number? And so that was this graph here. And so, so this graph basically in the smoothing delay, we have to come up with a number to tell Vensim for what the smoothing delay is. Like Vensim will say, all right, Vensim, we want this output to be a delayed version of this input using a delay of 2.5 seconds. Well, where the heck does the 2.5 seconds come from? Because the output looks different than the input. So how do I figure out that it's 2.5 seconds? And if you wanted to look at that, if you're looking at, at data, real data to figure out how, what to put into Vensim, the number it's expecting is a number which corresponds to the time it takes for, if you were to make your input, this so-called, and I'll make this, let me change to a pen here. If you made your input into your toilet or your system a so-called step, so that's this square input here, this is a step response. So if I go to my real system and put a step into it, I put the input, I make it immediately change. How quickly does the output change? And then so I look at the output and I say, well, I put the step in at time 1 and I watch the output change. And the time that Vensim or InsightMaker uses for the smoothing delay corresponds to the time it takes for the output to reach 63.2% of the final value, or in other words, of the kind of input value here to this step. So I can see the final value here is 1. So I see that 0.6321, that's the value I'm looking for. And so at 0.6321, which is 63% of the final value, then I can see that that occurred at time 3.5, which is 2.5 seconds after when I put the step in. So that tells me that the time constant of this smoothing delay is 2.5 seconds. And where does this come from? This is a version of half-life. So we don't use half-life because in order for us to use half-life, it would require us to use equations that make a lot of use of the natural log of 2. And so the equations that go into a smoothing delay end up basically being like, it's kind of like with the bacteria example of bacteria death. We say that the death rate of bacteria is the number of bacteria divided by the time constant. In order for us to use a nice division there and don't have to add in a bunch of natural log of 2s and things like that, then we have to use this 63.2% number. And so that's kind of where that thing comes from here. So it's just, you can think of it as kind of a scaled version of the time of the half-life, where the half-life would be like the time it takes for this to reach 50% of its final value. But instead, we're saying it's the time to reach 63% of its final value, which in this case was 2.5 seconds. Does that make sense? It seems a bit arbitrary, but it makes the equations simpler if we use the 63.2% when we take data from the real world and calibrate our simulations. I'll assume that's good. Or are there other questions about that? All right. So the SIR model, this is a sort of a very kind of famous system of dynamics model that's been useful in coming up with kind of a conceptual version of what goes on in about any kind of disease spread. This is where the so-called R0 number that you hear about in the news and on current events now, but also movies and things like that. And it comes from this idea that you have 3 compartments: a compartment of susceptible individuals, a compartment of infectious individuals. So 4 just uses infected, but they're technically infectious in that they're spreading disease. And then recovered individuals. And so this is an example of a multi-compartment model where we divide a population up into 3 groups and we keep track of how big those groups are at any time. And so we then need to say is that based on the current number of the individuals in this group and in this group, what do we expect the growth of this group to be, and what do we expect the decline in this group to be? And that's what we form equations to do. And then we also need to say is that based on the number of individuals in this group over here, then how do we expect the decline of this group to be and the growth of this group to be? And so that's what the SIR model models. And so I'm not going to go through this in detail like we did when we first went over it, but I will say that it's a great idea to review the SIR model because it makes use of a lot of constructs we see in a lot of other models. And so even models we've seen before, like the bacterial model, and the models we've seen after it, like the vast diffusion model. So for example, in coming up with the formula for recoveries, I would definitely try to be comfortable with this formula, where we're saying, well, how do you figure out the flux of individuals from the infected compartment to the recovered compartment, from one group of the population to the next? And it's all based on the average duration of infection, like I was just talking about, which is effectively a smoothing delay. So we're saying that the number of recoveries, this flux here, is going to be equal to the infected population, which I'll draw a little causal link there, the number that are currently in the infected population, and then divided by the average duration of infection. And so basically we know that every individual in the population contributes a recovery, so 1 recovery per person, after waiting an average of this many duration of infection. And so this duration of infection, this is again the average time that an individual stays sick. So that is what gives us the total number of recoveries per day at a population level. So we can simplify that to just be, and again, it's effectively adding in this arrow here, that the number of recoveries is the current number of infected divided by the average time that each one of those are infected. And so that also means that we need to introduce a little parameter up here that you can imagine putting a slider underneath, and those two things are needed in order to formulate this recovery flow here. And this recovery flow is a balancing feedback. And how is it a balancing feedback? Well, we know that there is an implicit negative link going back this way, because an outflow is always taking away. If you increase an outflow, you decrease the stock that it's connected to on the back end. And so this plus here, we're saying that if you increase the number of infected individuals, you increase recoveries. But if you increase recoveries, you decrease the infected individuals. And that's what makes this a balancing feedback. And so I would make sure that you feel comfortable with that characterization, that this process here is a balancing feedback process. So are there questions about this simple little nugget? I don't mean to say simple, about this sort of small piece of the SIR model, because this is sort of fundamental. So if there are questions about this, then there will definitely be questions about other things. So I want to make sure there aren't questions about this. Okay. So skipping a little bit ahead here. So we can do that same game for other processes here. So we know that, you know, that we walked through the kind of derivation of all these different loops. And so there's the recovery loop, which is that balancing feedback, which is kind of hidden up here. There's a contagion loop, which is basically the thing that says that whenever infected individuals bump into susceptible individuals, there's a certain probability of them spreading disease. And as they spread disease, you decrease the susceptibles and you increase the infectious. And as you decrease the susceptibles, you're going to actually end up making it less likely for there to be future infections. And so that's the depletion loop, because you're depleting the number of susceptibles. And so basically the number of infections is positively related to the number of susceptibles and the number of infecteds. And so this net flow this way, as it's increasing the number of infected, it's also decreasing the number of susceptibles. So eventually it ends up decreasing the number of infections, because you end up pinching down this infections because you end up reducing the number of susceptibles. And that is what relates to the magical herd immunity that everyone kind of talks about. And then we also talked about how using these models, we can start testing policies. And so in this particular example that we walked through back in Unit E, then we said you can model quarantine policies. And basically the way you end up modeling that is you can create a lookup table which relates the number of infected to what previously you might view as a parameter, the number of contacts per day per infected person. So instead of that being a parameter where you just sort of assume it's one constant thing, you can say, well, if we implement quarantine, then when you have a certain number of infected individuals, the quarantines kicks in, and that's going to reduce contacts per day. But under that trigger threshold, then the contacts per day is whatever it normally is. So you could build a little lookup table, which basically has the infected population on one axis and the contacts per day. So the contacts per day per infected person on the other axis. And you can imagine that it's maybe high, but then you reach some critical threshold and then it jumps down, and then maybe you reach other thresholds and it jumps down even farther until eventually everyone is just locked in their house and it's basically down here at 0. So you could, experiment with different quarantine policies through the lookup table. And that's basically what they did in this example from Andy Ford in his textbook on system dynamics modeling, is that they basically, for that lookup table, they had a version where the lookup table was flat. You had always the same high number of contacts per day. They had another lookup table where at 2,000 infections, they have the contact rate. And then a third lookup table where only at 1,000 infections, they have the contact rate. And what they showed here is that you get a flattening of the infection curve. And so that might mean that under these two scenarios, you go over the hospital capacity. But under this one scenario, you actually weather the storm, and you don't ever go over hospital capacity. But this one scenario, people continue to get infected for much, much longer into the future. So as a consequence, if you look at the affected population by this disease, then under all three quarantine policies, you get a very similar amount of people that end up getting sick. But under this third one, as we saw on the previous slide, we can make an argument that that we don't overwhelm the hospitals, because our model assumes that the hospitals will be able to treat people. But in these here, if we go over hospital capacity, the fatality due to the disease here might go above the fatality that we might assume in our model. And so that might be an argument for why, even though it doesn't appear like we're actually reducing the number of individuals affected by the disease, we actually are keeping the infrastructure intact, which we cannot guarantee with these two. So that's kind of the way you can make an argument using this SIR model. All right, so are there questions about the SIR model and the types of arguments you can make with it, the dynamics that go on? Okay. All right. So relating to all of that, we talked about the BAS diffusion model. We talked about growth and diffusion in general, and how we saw growth and diffusion in the fish stock, the harvest model here. And I talked about how there are alternative ways that we can model these fish stocks. So this was the single fish stock of fish that are actually in the fishery, and there is a net regeneration rate that goes that below a maximum sustainable yield has an increasing slope, and above the maximum sustainable yield has a decreasing slope. And that's all modeled by this lookup table here. And I said the downside of that is that there's an obvious feedback loop here, but the direction of that feedback loop, whether it's positive, whether it's balancing or reinforcing, is contingent on where things are in the simulation. And we generally don't like that. Like, so if you can add more details so that your feedback loops always have the one direction, then especially even your arrows, like your causal links always have one direction. So like right here, fish stock into fish density, well, we know that's got one direction, but then fish density to net regeneration. Well, we know that for these ones here, if the fish density goes up, the net regeneration rate goes up. But for these over here, if the fish density goes up, the net regeneration goes down. So label this link with a plus or a minus. It's unknown. So we would like to kind of fix that. And we said that one way you can fix that is by reconceptualizing this growth model in terms of the current number of fish and the remaining fish that could, in principle, be added to the fishery. And there is a way of building an equivalent model that uses these two things. Oh, it's got muffled. I can switch microphones if that'll help. This. Is that any better? All right, I apologize for that. I'm not sure what happened there. Okay, and thanks for, okay, great. Thanks for letting me know. Please let me know these things as soon as you can. I want to make I want to make my long droning lectures as well, the least painful as possible. So let me know when that stuff happens. But so it's basically said that we could potentially come up with potential fish. So they call this PF, potential fish, and then real fish. And by doing that, then we can say that the real fish always have a reinforcing effect on birth rate, and the potential fish always have a balancing effect on birth rate, because as you have more births, you actually decrease, because remember there's an implicit negative arrow here, the remaining fish that could be added.
And that's what gives you this balancing effect. And so now we've split these things out so that we can look at this model, and regardless of what the current stocks are, we know there's always balancing and there's always reinforcing. And that's effectively what they did in the Bass diffusion model. And so the Bass diffusion model is kind of based on the kind of SI side of the SIR model, where they have susceptible individuals are our potential adopters, like our potential fish, and infected individuals are actual adopters, are sort of true fish. And so they refer to this as kind of a contagion model. And because of that, when we look at the details of the Bass diffusion model, you see a lot of things that look exactly like the SIR model. So there's kind of this, oh, I went too far. There's kind of this thing where we've got our contacts per day. We've got our infectivity, which is the so-called adoption fraction. So it really matches this SIR model really well. The thing that's novel about the Bass model is that they add advertising, where so there's this, if you have a large number of potential adopters, then you end up getting a strong effect of advertising. That sort of gives you a starter motor to this engine. And so that starts the adoption rate up, but then once you have a lot of adopters, word of mouth takes over. And the word of mouth process is kind of this WM word of mouth. That's kind of what's going on over here. And that is really where you get most of the growth from your product. And so that's kind of the Bass model. And we talked about various variations in the Bass model where you can bolt on different aspects to it to make it act in different ways. But the basic structure is still there. So are there any questions about that, about the Bass model, about growth and diffusion? How the Bass model effectively takes the kind of a fisheries model and adds advertising to it, as if sort of if there were no fish in a fishery, there was some process that would sort of get the fish going in their reproduction very quickly and then allow them to take off after that. So that's kind of like, you know, so there's the Bass model in some ways is very similar to the fishery model, except the fishery model doesn't have the advertising piece, which the only thing I could make an analogy to be somebody stocking the fishery when it's empty. That's kind of like the advertising model. Okay. All right, so so then we talked about unit F, and I hope, you know, answering a question from way back, I hope you can see that, like, in walking through unit E, then what we really see is that we're using stocks and flows and all that stuff that we talked about pre-midterm. I didn't talk about the time step, you know, that sort of thing. But in reality, you know, we're just making use of the fundamentals that we build up pre-midterm. And so it's really, you know, although all I just talked about was post-midterm material, it used a lot of what we learned pre-midterm. All right, so in unit F, we just make things a little bit more complex. You know, we learned about the tipping point, which I think a lot of you have talked about tipping points in your other classes, at least those of you who are sustainability students. And then we talked about building confidence in our models. So these are things like boundary adequacy, structural adequacy, dimensional consistency. Those are things we talked about there that were kind of important for you to think of. And so I, you know, might skip over a lot of this stuff here. You know, the big thing here was this process of where we kept talking about dynamic hypotheses, about making use of these basic archetypes to sort of help us come up with these hypotheses. So if in data you see an oscillation and you're not quite sure, you know, what could have possibly generated those oscillations, then that suggests that maybe you think about, are there important structures in all of the variables that you could think of that could possibly affect this system that are connected together as a balancing feedback loop with delay. And so that's kind of an example of using the archetypes we know about to help jumpstart our ability to build causal loop diagrams and then stock and flow diagrams. And so, you know, we can use those balancing loops with delays to set up things like market pressures, you know, sort of basic examples of microeconomics, but then we have to bolt onto them other processes to account for things that deviate from those oscillations. And so that's why we talked about this model of OPEC. Again, I'm not going to ask you about details about OPEC, but this basic idea that that when we looked at real data sets, we not only saw oscillations, but we saw oscillations that sometimes had were very wild as well as very rapid, and then also regions of stability. And the simple balancing feedback with delay really only explained this part, which told us that we might probably need a portion that's like that, but we also needed to add in some other things to explain the stability and wild oscillations. And that's kind of why we went through that case study with the oil producers. And then we talked about the public sector applications, and that kind of brought home this general process of coming up with a dynamic hypothesis for sort of explaining a system's behavior. From there, choosing your stocks and flows and building a coordinating network that's consistent with the dynamic hypothesis. And so I see oscillations, so I'm looking for balancing feedback with delay. I'm going to choose stocks and flows that I think are important to my system. I'm going to connect those up in a way that's motivated by my dynamic hypothesis. And then that is going to be the basis of, wow, I think the system is working. Now, in order for me to actually see if I'm right, I need to test my hypothesis. And so what I do is I build a simulation using the stocks and flows with the coordinating network that I put together. And I look at the simulation's output and I see if it looks like the real output. And if it does not, then that tells me that my dynamic hypothesis is probably not the one that's operating, and I need to modify it in order to really see what's going on in the real world. So that this dynamic hypothesis might be a simple explanation of what's going on that maybe is someone's pet theory. And by going through this process, if I reject that, then I could say, sorry, your pet theory, it sounded plausible, but when we simulate it, it doesn't give us anything that looks like reality. So that must mean that there's something a little more complicated going on. And we kind of went through that process in that textbook chapter. Again, I'm not really that worried about you understanding the dynamics of urban growth and stagnation, but I do want you to understand this basic process of starting with a causal question, generating a hypothesis, using a simulation to test, to generate predictions, and then comparing the simulation results to reality to assess whether your hypothesis was a good one. Okay. And those tests may look something like this. So here's real data, and here is simulated data. And when the simulated data looks so similar to the real data, then that gives us confidence that we can use the simulated data as a proxy for the real system. And as we sort of do surgery on the simulated system, we end up actually maybe learning about what's going on inside the guts of the real system that we can't do surgery on. Okay. So any questions about any of this so far? And this is kind of looking into the guts of it. So with the fishery model there, trying to understand why, in a real world system, things are fine when you deploy 10 boats, but then suddenly after you go to 50 boats and then you go back to 10 boats, things aren't fine anymore. It's hard for us to wrap our heads under why 10 boats later is not good, even though 10 boats sooner was good. And we use this example from the text with the fisheries to say that, well, once you've crossed this so-called tipping point, then it changes the dynamics of the system so that after you've crossed the tipping point, you may actually have to go to no boats and wait for a long amount of time before you can go back to the previously safe amount of boats. And so that was this, this tipping points idea, which I can go through the tipping points here. But based on the muddiest point notes, I got a lot of people that sounded very familiar with the tipping points. So maybe I'll jump ahead for time, but I'm happy to take questions on the tipping points. But I'm just there's kind of my tipping point summary slide there. So are there questions about tipping points, or the types of complex phenomena that we talked about in this unit. I do want to say that when I have time in these units, I talk about something called bifurcation diagrams. And so there are some slides that I have in these review slides that look like this one. And if you look at the test exam, the sample exam, I think I might have asked a question or two about bifurcation diagrams. I didn't have time to cover that in this class, and it was always kind of bonus material anyway. So I'm not going to ask you about bifurcation diagrams. If you're interested in bifurcation diagrams, which are slightly more advanced way for us to characterize tipping points that if you continue in dynamical systems, you'll definitely see again, then I've got lectures online that you can watch where I go over these bifurcation diagrams, but I'm not going to ask you about them. So if you see one in the sample final, don't freak out. There are no questions on the upcoming final about bifurcation diagrams, even though there are some slides here. So with that in mind, do you have any questions about tipping points? And then don't worry about bifurcation diagrams. Okay. All right. So then we got to the end of that unit, and we talked, we kind of, came full circle and talked about models as transitional objects. So to just generally understand what I mean by transitional objects, understand what we mean by illusions of depth, this idea that people can feel like they understand how something works just because they know how to use it. But when you actually ask them to form a model of how it works, then that can expose that they had an illusion that they knew how it actually worked. And you can get inconsistencies that way. So the model building process, by just building models, teaches us what we don't know and helps us deal with inconsistencies in our own mind. And so it can be, even before you run a simulation model, building a simulation model can highlight when there are inconsistencies in your understanding. And that's kind of a key point that I was trying to get when I talked about these illusions of depth. Yeah, and so I'm just kind of skipping through some of these slides here. And that kind of brought us to the more formal stuff from the chapter. And I would say these confidence building tests, these are kind of important ones that I would make sure you're comfortable with, particularly this middle column, the difference between so-called boundary adequacy, structure verification, dimensional consistency, the extreme conditions test, and your kind of parameter verification. And, and I would even further maybe highlight the differences between these three. So these are kind of the gut checks you do every time you build a model. Boundary adequacy, did I include everything? Structure verification, are the equations I used, including all of the influences that they should, among the things I chose to include? And then dimensional consistency, of the equations I put together, if I put all the units in, then do I end up getting the expected units out? Because if I don't, then that might mean that I didn't craft my equation properly. Maybe I multiplied when I meant to divide. Maybe I accidentally put the reciprocal in for a parameter when I meant to do the other way around. So are there questions about these, boundary adequacy versus structure verification versus dimensional consistency, or these other ones here? But mainly, again, I'd focus on this middle column. Okay. And then getting towards the end of the class, sort of our last lecture before Eric's lecture was just, figuring out the difference between randomness and chaos. And this is kind of the big punchline. came from this, this right here, is that randomness or stochasticity is a modeling tool that simplifies model building, whereas chaos is apparent randomness that emerged from non-random systems. And so that was kind of what I was hoping that you would take away from that. And I introduced this term stochastic modeling, which comes from the Greek for guessing or conjecturing. And it's this idea that even though a real world system in theory operates deterministically, because we don't have access to all of the information that we might need to make accurate deterministic predictions, and even if we did, the formulas we'd have to come up with would be enormously complicated and difficult to form and then simulate. Instead, we just say, well, let's pretend like we don't have all those details and just see, can we coarse grain that system with a random representation. So I have no idea when people are going to arrive to class. I could know everything about all of you and then use that to predict when each one of you is going to arrive. Or because there's no way I'm going to get all that information, and that's creepy if I would have that information, but even if I did get all that information, it would be very difficult for me for a very large class, like a class of 300 students, to figure out, to plug all those things in and to keep track of all 300 of those. So instead, what I do is I say, on average, people arrive a minute before class, and there's some variance where some arrive 2 minutes before that, and the other arrive 2 minutes after that. But generally, almost nobody arrives 2 minutes, after that 2 minute mark, and almost nobody arrives before that other 2 minute mark. And so there's going to be a random set of arrivals between -2 minutes and 2 minutes. And so if I model the arrivals as being random on average 1 minute before class, then I get just as good a prediction as knowing all of the information about everybody. So that's the idea of a stochastic model, is I'm replacing deterministic knowledge with a random approximation. And that ends up making it much easier because I don't have to include as many variables. It reduces the boundary adequacy I need to live up to. And with fewer variables, there's fewer connections between variables. And so I don't need complicated equations. So it reduces the variables and it reduces the complexity of the equations that use those variables. And so we gave examples that I just gave you another example of that. And then the advantage of these things is with stochastic modeling, instead of getting the nice smooth trajectories that you all are getting in your final project reports, we can instead get realistic trajectories that if we run the model over and over again with different random number seeds, we get slightly different trajectories. We run enough models and take the average, and the average will collapse to exactly the model that we've got using a deterministic approach. But we get realistic variation from each individual run, so that it makes the models more realistic, even though we've introduced randomness, which may itself be less realistic. So that's stochasticity. And the only other thing that we talked about then is chaos, where I said it was an extreme sensitivity to initial conditions. You don't need to know the Mackey glass model or the Lorenz attractor or anything like that. All I'm trying to get you to understand is that with a stock and flow model, as simple as this one, simple looking as this one, you can have it so that a small change in the initial conditions for this stock is going to create long-lasting differences in the behavior over time that look like random noise. But in reality, if you knew more about the system and how it was running, you could predict every single one of those, even though they look like noise. And so that's chaos. And there are pretty visualizations like the Lorenz attractor that we can get that help bring sanity back to that, so you can start seeing the structure in the chaos. And that's sort of all the post-midterm material. And so I have to stop there because we're at 4:15. But at this point, if you were to continue on in these slides on your own, you would find that we just start back at the beginning, and again we've got all these learning outcomes, which I recommend you look through these learning outcomes and treat this as a study guide. Make sure you can do all of the things that the learning outcomes ask you to do. And so with that, let me just give you all your last attendance question at the very end here. So there I'll put the link there. And in the question here, I will say, what topic most worries you about the final exam? And so go ahead and put that in your attendance question, and that will be interesting for me to look over. And otherwise, I'm happy to stick around for a few minutes or so if you do have questions, but otherwise, if you don't have anything else, then you can feel free to head out. I will have office hours as usual Thursday, but that's going to be, during the final exam day, and I can't answer questions specific to the final exam. So if anything does come up, then just send me an email or send me a Slack message, and I'm happy to answer your questions there. But try to get any content-based questions out before the final exam, because I can only sort of answer kind of formal things on the day of the final, because I don't want to accidentally squeak out an answer that might help you on the final exam and not help the other people who didn't ask. So anything else? Questions? Concerns? And if not, if this is the last time I see you, then I hope you have a wonderful summer, and I hope you feel good coming out of the final project, which I'm really excited to see your presentations. And again, final exam on Thursday, stage 1, stage 2, the collaborative version on Tuesday of finals week. And make sure you turn in your peer reviews, which are, you do get a portion of your grade from completing those peer reviews, and those are due Saturday night. Oh, and student evaluations of the course and of the TA. Don't forget about those links. I think you only have like 2 more days to get those done, if you choose to do them. And thanks for your comments, and thanks for your muddiest points in particular. You guys have been really excellent filling those out. They've been great to read every week, and I hope my responses have been useful. Oh, and yeah, and sorry that there's no Dexter today. I don't know where he is today. Thanks, everybody. All right, looks like things are trickling out, so I will go ahead and end the meeting. And again, feel free to keep in touch if there's any other questions. See you.